I guess I'll start up for the second half. Umut mentioned a web page you can go to that has our notes, and I just typed in 15.2.10 and hit return, and it showed me this, but it could be biased by my own previous searches because that's what Google does. But does someone want to try that? Does 15 course come up top for them, or is it just me? Okay, it seems to work for other people too. So you can go there, and in here there's the under the schedule is actually the all the course notes. Oh, it's not in here. It's in previous semester. Oh, I see. Yeah. Okay. Yeah. So there's all the course notes if you go to PDF, etc. There's also the library, which is this library that Umut's been talking to, the sequence library. So this is all done in the context of SML, standard ML. And so there's a signature for it, and there's actually 3 different implementations. There's array sequences, which Umut was talking about. We also have the exact same interface implemented with trees, and the exact same interface implemented with lists. Obviously, the list one is not parallel. The tree one is parallel, but has a somewhat different cost model. So you can go in there, and in fact, if you click on these, it will tell you various things. So if you go click on sequence, you're going to see all the operations that Umut talked about today, including iterate and iterate prefixes, reduce, scan, split mid, subseq, a bunch of different operations. If you click on that, it's got the type, and if you click on them, it gives you some description of what they are. And if you go into the implementation on the particular, then it gives you the cost model for each of these. So here's the, it tells you the work, and if you scroll over the span for each of the different operations. So this is what the students see, and so they can know when they're analyzing algorithms what they are. Okay. And then we have other sorts of data types, table sets, priority queues, etc. So we have a, reasonably, at this point, polished, we've been working on quite a few years, implementation of these sequence libraries with all the costs written down. So that's the, you can go to that web page, and it also has a course note. So if you go to the schedule and you go to scan in here and click on the PDF, you'll find basically the code for scan and a description of it, etc. Okay, what I wanted to do is give you a little demo, because some of you might say, oh, this is all great in theory, the lambda calculus, that's like for theoreticians, not for practitioners. Of course, you're here mostly PL people, so maybe you don't believe that, but a lot of the audiences I talk to say, oh, that's all for academics, right? Someone asked, well, does anyone really use functional programming? And the implication there might have been, well, is this really work or practical? So here's just a simple example of a piece of code using exactly the operations. I'm showing it because it's using exactly the operations that Umut talked about. This is just numerical integration, right? So it takes a function f. There's a great thing to do with a functional language because I can pass this function f. It's an arbitrary function, and it evaluates it at endpoints between s and e. So S and E are the 2 endpoints on the number line, and I'm basically it's an approximate numerical integration. It's going to evaluate it evenly across that at n separate points, add them all up, divide it by the right amount so that you get this numerical approximate value of an integration. And you pass it in any function. So basically you tabulate, you just evaluate the function at a bunch of points. That's the Fn of I. We all know Fn is just a lambda. So we evaluate at the appropriate points, and then we sum up the result with a reduce. Okay, so is it clear that what this code does? Any questions? So that's just numerical integration. And then you have, here I'm just applying it to an example. I think in this case, where do I actually have the function? Integrate. Oh, here, right. So the function I'm going to apply it to is this f of x, which is, the sine of x plus times the square root of 1 over x. So some arbitrary function, just to show I can apply it to any other function. And then in my example, I take it and I apply, it's just where I apply it, right? And then I have some code for timing it, et cetera. So I'm integrating that funky function from 1 to 1,000 at n points. An approximation. Shoot, okay. Okay, so I've compiled this ahead of time. In fact, let me make sure it's not compile. And so what I can do now is run that code. Okay, and it's set up, our system is set up, we've got this version of Milton. The students actually do most of their code in an SML of New Jersey, but we have a parallel Milton implementation, and it basically parallelizes everything. So it takes that tabulate and parallelizes and reduce, basically using exactly the sorts. It uses a work stealing scheduler, like I talked about yesterday. It's basically using all the approaches we've talked about so far. Okay, so if I run here, I'm just running the code I'll show you. Okay, and I can specify P as a number of processes I'm running it on. So it says one thread. I'm running it on, I'm evaluating it at 100 million points. Okay, and I guess I'm running it for 5 rounds. That tells me what the integral is. So it turns out the result of that integral is approximately 0.6149. And it took 4 seconds, okay, to evaluate that integral. And then I could say, well, let's run it. If I don't give P, it runs it on the maximum number of cores. How fast do you think it'll run if I run this in parallel? What? 1 second. Good. Someone asked the right question. How many processes is it running on, right? Because we have this whole W over P plus D, okay? Now, ideally, we'd like it to be exactly W over P. In reality, it's very hard to get exact linear speed up, and this is true with any programming language. You can ask, anyone you talk to. It's very hard. So it turns out this machine has 72 cores, okay? It's not hard to get, how big is a machine with 72 cores nowadays? Yeah, it's this big, right? It's a rack-mounted machine, nothing special. In fact, the most expensive part of this particular machine is not the cores, it's the memory, because we have 1 terabyte of memory in this machine. It turns out that by itself is $15,000. The processors are maybe $12,000. And so this is a reasonably modest machine. Okay, you might not carry it around with you like a laptop, but you could certainly have it in your lab or something. 72 cores. Nowadays, we bought this when it's 4 chips of 18 cores each. That's how it's configured. Nowadays, you can get 28 cores. So we bought this a year and a half ago, and I think 18 was the most you can get. Now Intel makes the 28, so you can get 4 of 28. Okay, would be the equivalent modern day of this. And this is increasing every year. It'll be 36, 40, and it's going up. So, we'll soon have hundreds of cores, right? This is 72. So how fast, now that you know it's 72 cores, how fast do you think this will run? Let's hope my demo works. It could be someone else on the machine. Let me actually do something here first to make sure I don't. Okay, no, uh-oh, someone is running something. Okay, now it's not, okay. It was just top. I think that's not, okay. Just want to make sure no one else is running a big job when I do this. So what do you think? This is 4.4 seconds. How? 1 second? 0.6. 0.6. Tenth of a second. You guys don't trust parallelism, do you? Okay, 0.06. Okay. That is how fast, did someone have a calculator? Divide 4.4 by 0.0, let's take the fastest one, 0.0617. 73. Why is it getting 73 when it only has 72 cores? Can someone tell me? Does someone know something about these machines beyond the number of cores? Not caches. These are hyperthreaded cores, so they have 2 threads each. So it's 144 threads. Now it turns out that you don't, having 2 threads each doesn't help you by a factor of 2 because they're all contending, they share registers, they share arithmetic units. So when you go from 72 threads to 144, you don't get linear speed up anymore, but you do get some speed up. So in something like this, we're seeing more than speed up than the number of cores. Okay.
How much do you get with 8 processors?
Well, you get 8-fold, you get 8-fold speed up, right? Run minus P8. So what would 4.4 divided by 8 is what? 0.55, is that right? Or something like that? Yeah, 0.56, right? So it does what you expect it to do. It gets this speed up. So I just wanted to show this demo so you don't think this is all smoke and mirrors, that you actually can get speed up. Okay. I should point out there's this other thing we did, which is, and it's actually available off this site here, if you, 210. We had this competition for our class. In fact, it was open to all of CMU. It was a sorting competition. So they had to basically write a sorting code, and we had a specific spec. It had to be a comparison sort. It had to be on 100 million elements. We actually gave them the function for generating the inputs. The elements were actually pairs of values, and they did comparison on the first, and so you basically carried around the second element. So it was a pair of 64-bit value, basically a pair of doubles is the type, and you could write it in any language. And the first prize was one of these. So a brand new Apple laptop, a $2,000 laptop. And what we did is we did our own code. We wrote a version in ML, in our language. And I should point out there's a tiny bit of cheating here, which our code wasn't 100% purely functional. What we do in the class is 100% purely functional. We did have a couple side effects in here. We think we can get rid of them. And then we also wrote a version in C++. We think this is probably the fastest sorting code out there, the C++ version. Our version on this particular input ran in 0.33 seconds on this machine with the 72 cores on 100 million keys. The C++ is 0.18 seconds. So indeed, C++ is a bit faster. Okay, and this is a highly optimized parallel version. We had submissions in all different languages. In fact, we went to Doug Lee, who's the person who wrote the Java fork join framework. And Vijay mentioned him yesterday a few times. And he also wrote the parallel sort for Java. And so we said, well, can you enter a competition using your Java sort? And you can tune it or whatever you want. It turns out the Java sort on this problem ran in like I'm saying, the C is 0.183, ML is 0.33. The Java ran in 1.4 seconds. So 4 or 5 times. And this is Doug Lee is the expert on parallel algorithms for Java. There is no one that knows more than him. He wrote the whole parallel library. He wrote the fork join interface. And
Factor 5 slower?
Yeah, factor of 5. So, and now it turns out, can someone guess why it was so much slower? Java can't unbox pairs. It just semantically, it's not allowed to. So we then tried it with just floats, and theirs ran in about 0.6. So it's still slower, but at least it was more reasonable. It turned out that the winner, the one that came closest to ours, which was still not nearly as fast as even the ML. By the way, one rule is it had to be a garbage collected language. And it couldn't be one of the two that we gave, so it couldn't be ML or C. And C, of course, is not Java, it's garbage collected anyway. And so the winner was a program in Go, okay? And it ran in 0.5 seconds, so about 1.5 times slower than the ML. And so it was Go with parallel primitives, etc. And that was, so someone got a laptop for that. So the point being, again, it's not easy to beat SML. Okay? It can't be done with Java. And now, of course, Java is not exactly an efficiency language. But, you know, so, and the nice thing, this is all done with the Milton compiler. And by the way, the Milton compiler is a really good compiler for this sort of stuff. Okay, the SML of New Jersey, even if you run it sequentially, we find SML of New Jersey, I mean, ranges depending on the type of code, but it's from like 2 to 10 times slower than the Milton compiler. Okay, so anyway, I just wanted to give you a slight demo of show you how it works. And if you want to, you know, we don't have the prize anymore, but for, you know, fame and glory, you want to enter this thing is if you just go to our web page for the 210 and, you know, put sort.html, you can find this batch. And if you think you can beat this in your favorite language, we've sent people off to try it in Haskell and lots of languages. No one's come close yet. But if you think you can do it, we encourage you to do it. The whole description of the input and what you need is all on the web. Can you what? No, unfortunately, we don't have another free laptop for you. Like I said, fame and glory. We'll put your name up on the thing, on the page. Okay, so I think that's all I was going to do with the laptop. Mm-hmm.
Is the runtime that you use available smart?
It is, but it's a, I'd say it's a beta runtime, and maybe even alpha in the sense. It's ongoing research by our research group. In particular, Umut's been working and one of his students. And so it's changing all the time, so it's not stable. But if you want to try it out, we can certainly give it to you. We just, you know, if you get some sort of core dump once in a while, I'm not sure we can promise that's not going to happen. But it is like I said, we've implemented a work stealing scheduler under the hood. The part we're working on now is the parallel garbage collection. That's actually the most challenging part of this, is getting parallel garbage collection. So it turns out the particular demo I showed doesn't do any garbage collection, so that's maybe good for us. But because it's just this giant reduce. So you well, you don't even need to allocate the array, because you're just doing this tabulate, which sort of generate things on the fly, and so it's much cheaper. Okay, so that's all I was going to do, and I'm going to now move to the whiteboard. So let's see if I can figure out how to get this to go up. I guess just going up without turning the projector off is not particular. What? Oh, there's an exit? Okay, I think we need help. Okay, thanks. I guess just before I go on to the new stuff, the last thing Umut did was this scan operation, and he pointed out that if you, by contraction, what you do is you pairwise add them up. You get these three values. You do a scan on them. It gives you the basically these values, the 0, 1, and the 10, and then you squeeze in the these values into those places. But he didn't actually mention how do you figure out that this is a 1, this is a 3, and this is a 10. Can someone tell me how do you actually figure out these values? Squeezing them in is not hard. You can do a tabulate, and just like the append, where we either picked from the left or the right, we can tabulate, either pick from these elements, the result of the scan, or from these. So let's say I was able to magically generate the other ones, right? The alternative ones are the 1, this one here, and the 10. And then I just want to interleave them. I just want to take 0, 1, 1, 3, 10, 10. And that's trivial to do with a tabulate, just like the append. But how do I generate this 1, 3, and 10? Can someone tell me? So I know I've already generated this C, so remember I pairwise added these up. That gave me the 1, 9, and 5. I ran recursively a scan operation on that, something half as big. So I end up with a recurrence that looks just like the one for the contraction version of reduce. So I'm now going to, of Wn is going to be something half as big, plus order n, because I'm doing order n work to do these add-ups. So this ends up the total work. Plus I have to do some work at the end here to interleave that's also order n. So the total work is order n. But I have to generate this 1, 3, and 10. How do I generate the...
You can take the odd positions, and so in the top you have taken 1 and 0. Instead of that, you can take 0, 2, 7, 0.
And what do we do with those?
We'll generate the same, we'll do exactly the same thing what we have done. Then we'll sum.
Good. If we do that, then we'll end up doing another recursive call, right? And then this would be 2 times W of n over 2. And this would be n log n. So it works. And that's a very good observation. Great. That actually definitely works. What we can do is, we've generated these, and I'm not going to go through the exact details, but we could generate these other ones in a similar way by making another recursive call to scan. And we'd end up with a recurrence like this. But we want it to be linear. So I don't want to make more than one recursive call. I want to make just the one recursive call to scan. So what is this value? Is there 2 values that I already have that I can use to get this from? Are there 2 values I already have to get that from? So this here is the sum, the 9 basically, right? It's the sum of everyone up to 0, 1. Oh, is that supposed to be not? Oh yeah, sorry. This, what I'm saying is this 1 is the sum of the first two positions, right? This 10 is the sum of the first 4 positions, right? And so I know the sum of the first 2, the sum of the first 4, the sum of the first 8, the first sum. I know the sums of every even. So if I know the sum of the first 8, how do I get the sum of the first 9? That's it. I just do a trivial add. So I add this 10 plus 0, which gives me a 10. I add this 1 plus 2 will give me the 3, etc. Right? I add this 0 plus 1, and that gives me the 1. I have the sum up to every even. I just have to one more. So it should be clear I can do that in constant depth span, because I can do that trivial in parallel and in linear work. Yeah?
If we will do this way, then we have to depend on this particular computation to get.
We do. So if you look, the dependence is I have to, the code, I'm not going to write the code on board. I first have to pairwise add them up. I then have to make the recursive call to scan. And then after that, I have to then generate these things. I don't need to parallelize it, because I'm assuming that's sequential here. So if I look at the span, I say span of n equals order 1 for my initial singleton, plus I make a recursive call, which is order s of n over 2. Well, let me just write s of n over 2. Plus I then, notice I'm adding these. I'm doing them one after each other. Plus, I then have to do basically the summing up of these, and I also have to then interleave them. But that's another order 1. Right? So this is s of n equals s of n over 2 plus order 1. This solves to order log n. So it's fine that those are done in sequentially, because the parallelism comes from the fact that I'm doing all the additions in parallel. Here, and also when I generate these, I do all those in parallel. So I get linear, at the end of the day, I get linear work and logarithmic span, and that's basically the best I can do, because obviously this is a problem that's at least as hard as reduce, right? Because I'm actually sort of doing multiple reduces. I've done it in the same time. So in the exact same work and span that I was able to get the overall sum, I'm able to get all the partial sums, which is sort of amazing because it seems like, as Mut says, like a very sequential thing to do to get each of those. And this, of course, works for any associative operator. We're doing it with plus. It could work with append. We could basically have a bunch of sequences, append them all, and lots of different things. Okay. And it turns out scan. I'm going to show you some applications of this scan operation as we go further. So we wrote, during the break, we wrote a list of everything we've covered so far, along with the costs. And I'm going to be doing a few more operations now. And then I'll get to some examples where we can use this for a little bit more sophisticated piece of code. So the first one is update. Okay, so we've talked about reading an arbitrary element. What if we want to update an arbitrary element? So we just want to change the value of a particular location. Okay, now this is a functional interface, as someone pointed out earlier, so I'm not allowed to update in place. So I can't go into an array and just in constant time change its value, because that would not be persistent, it would not be functional. So really the only way we have to do this is by copying the array. Okay, so unfortunately, at least what we've described so far is going to force us to spend linear work to do an update, because I have to basically copy the whole array, do an update, and return. And that's nothing to do with parallelism. That's going to be true in a sequential sequence. If you have pure a pure language with sequences based on arrays, it's going to take you constant time, linear time to do the update. Now you could make it improve that by, instead of implementing them with arrays, you could implement them with trees. And in fact, if you notice, we had a tree interface, and indeed in the tree interface for sequences, an update only takes logarithmic work and logarithmic depth. But in the array-based one, it takes linear work. Okay, but you can do it in constant depth, so it's very parallel. And what we'll talk about tomorrow actually is a way to do it in constant work. Now, what it does is it's purely functional, but under the hood, it keeps track of, you can think of it keeps track of a reference count. It keeps track of how many people have pointers. And if it knows that it's safe to do it, if it knows that no one else is pointing to that array, then it does it in place. And it can do that under the hood. So the semantics are purely functional, but the cost model is non-functional. And in fact, we had a paper in Popple, I guess last year or 2 years ago, describing the details of the cost semantics for keeping track of when the cost is what. But for today, let's just do the inefficient version. So we have an update, okay, and its type is alpha sequence. Okay, by the way, it's very easy for us to get the ordering of the arguments of these functions mixed in backwards and forwards. So please give some leniency or point out if I do it in two different ways at different times. Okay, so we have it. It takes a alpha sequence, and a particular interface is alpha sequence cross and a pair of int alpha, and returns an alpha sequence. Oh, is this one not very easy to see? Or, yeah. I would prefer a blackboard, but apparently. Is that one better? Yeah, we'll see. So we have update, and I'll write it a bit bigger also. It takes an alpha sequence, a sequence of alpha elements, let's say cross, a pair of a int cross alpha, and returns a alpha seq. And it does the obvious thing. It takes, basically, this is an integer. It's that particular element. Okay. Someone before asked, well, what if the integer's out of range? Well, in our ML library, it raises an exception. But there's actually a very good question, because what is the semantics of an exception in a parallel setting? Okay. That's a whole other topic that's beyond the scope here, but you can write a very sensible semantics for parallel exceptions. Okay. You can basically combine them in a different way. So we're sort of brushing over that issue. Yes. So there is, that's the type, and it's easy to implement. And this is pretty much the most efficient way you can do it, which is not particularly efficient. You can say tabulate. Well, how could I do this, right? So this update takes, I'm defining update, and it's taking a pair of a sequence S, well, let me call it capital A, and an index value and that equals, this is fun. How would I implement this with tabulate? Say what? Yeah, exactly. I could basically, very good. So I can basically just check if better do a different index here. I'm getting in trouble with two. Let me alpha convert. Okay. So lambda j, and I'm going to basically say if j equals I, then I replace what's there. Otherwise, I return the exact same thing as what was there before, right? So I say if j equals I, then my new value v, else my old value, which is ai, and then this is on the length of a or something like that. They're just saying copy, which is really the best you can do. I'm just going to copy the whole array except for that one element, which is going to be special. Do I have a typo there? Where is it? Oh, good. Yes, good. Yeah, this would return me the same element everywhere, right? Thank you. My alpha conversion was wrong. Correct, yeah. Thanks. Okay, so I can do that. That's an update. And well, like I said, we're going to look at how to do that more efficiently later. We're going to get to graph algorithms like breadth first search, where in order to get an algorithm that's is work efficient relative to a imperative algorithm, we need to be able to do an update. We have to mark the visited node in constant work. And so we can't afford linear work. It'd make that algorithm way too expensive. So we're going to need to make that more efficient. But there's another very important operation. Oh, by the way, I should mention, so the work here equals order length of A. What's the span of this? 1. So at least it's very parallel. Right? We got to tabulate, so we can do this copy. The copying is embarrassingly parallel. Okay, we have something we call inject, which is basically just a multi-update. So it takes a alpha sequence, and instead of taking an int cross alpha, it takes an int cross alpha sequence. And so it's just a multi-update. It just updates. You've got a bunch of integer value pairs, and at each of those locations, it updates with a value. Okay. So there's one question you might have if I have a bunch of integer value pairs. Why that by itself might not fully define what this operation does. The integers could be the same, right? I could have a sequence which is A, B, C, D, I say update. My updates could be at location 0, update with a X. At location 2, update with a Y. And at location 0, update with a Z. Right? That could be an input. And so I have to define that. And the way we define that is the last one wins. So if there's a contention here, we're going to say this Z wins. It's sort of arbitrary. We could say the first or something. But and so then the result is if I apply this, if this is my first argument, then I apply, I'm basically now going to get X. I'm going to get Z in my first position because that one won. B is going to stay. C is going to be replaced by Y. And D is going to stay. Now, it should be clear that we can implement this in parallel, right? Because all of these writes on these machines, on these multi-cores we're writing, they can all write in parallel. There is a little question of how you break this tie. And because of the need to break the tie, I'm actually going to define the cost of this operation, of the inject, to be, it's going to be order m plus n, okay, because, let me write inject, takes a and a bunch of updates. So let me write that as order the size of the sum of the sizes of them, because this equals order size of a plus the size of the updates. And the span is, that's the work, and the span equals order log n. And the reason we throw this in is exactly this issue of how do we break the ties. And so there has to be some mechanism. And it turns out there's algorithms which allow you to do that in logarithmic time.
Log n is log of k.
Log, yeah, okay, good. So it's actually log of, typically doesn't make a difference, but it's actually log of u, yeah. Size of u. Semantically, so it turns out if we go back and we say which of our operations need to be primitives, we assumed that tabulate was a primitive, and it turns out that we need length and sub to be a primitive. We don't need subseq, we don't need any of these. In fact, we showed, Umut spent time showing how to implement those, okay? But inject has to be a primitive. Update doesn't. I just showed you the code for update, right? This is the update here. Okay. If I want to get these costs, it has to be primitive. Now, if I don't care about the cost, I can define it trivially as iterate. I guess Umut put the, in our library, the order of arguments is different, but I think he put the initial value first, a update, and where does the u go, I guess? Yeah, and you update u. I claim that that's the definition of inject. I'm basically going to iterate over one by one, updating these elements. And because I defined it to be the last one wins, this will be updated first, and then later on it'll be updated again with z, and indeed the last one wins. But this is sequential, right? It's not going to give me a logarithmic span. In order to do that, I have to make it built in. So these are actually the only operations, in theory at least. Now maybe in practice you'd be more optimal by implementing these at a lower level. But at least from a theoretical point of view, in terms of asymptotic costs in our cost model, we can build all these up in the bounds I've written here based on just these four primitives here. Am I missing any primitives? No, I think that's it. Yeah?
The subseq in order 1 to those operations.
Which one?
The subsequence, the slicing.
The subsequence, what we do is we layer on top of the basic arrays something that just returns. So the way I implement the sequence is with an I, the start, a j, and an actual basic array, which is not a sequence. This is an array. And this means starting at I and j. And it also gives me length, right? Oh, length I don't need, sorry. Well, I guess I need probably I need the length of the basic arrays, yeah. But this basically, right, so this says it's array A indexed from I to j. And that's constant time to do that, constant work. Okay, I wanted to show a couple more interesting ones. Okay, as in most libraries you'll find out there for functional programming languages, there's a function called filter. It's a very common function on sequences. In fact, it's in SQL, right? Filter's in SQL. It's in just about every array and library you can find out there. And what does filter do? I mean, the interface might change from place to place, but it takes a function f and a sequence and basically keeps all the elements in that sequence for which the function f returns true. So it's a Boolean function. Okay, so if we write down the type, the Boolean function is some function from alpha to Boolean, true or false, and it returns it needs to take the original, and then it takes the sequence, which is an alpha seq, and it returns an alpha seq. Okay. So has anyone here not seen filter in some form before? Okay. So the question is, how do we implement this efficiently? Okay, so if you go into the SML of New Jersey library, they have lists. As part of lists, filter is a function. Of course, it works recursively, linear, depth, span, completely sequential. So it's very easy to do this very sequentially. I want to do this in parallel. And I want to do it on our array sequences, right? So we have some sequence, let's call it A, B, C, D, E, and F. And let's say I apply my function to it, f, and maybe it's going to be true in some positions. So let me just put T and F for true and false. Maybe it's true there, it's false in these two. Maybe it's true in these two and false. Let me put a G here so I don't have two types of Fs. So that's just a map. So that if I did a map of F on S, let's say that's what it would give me. And so I now want to take these elements, and my output is going to be only the elements which I care about are the ones which return true. So it's going to be A, D, and E in this case. And let me just tell you ahead of time what my goal is. My goal is to get order. Well, can someone should be able to tell me what the goal in terms of work is. Because remember, our goal is always to be work efficient. So do no more work than the sequential. So let's assume, as we did in some other cases for now, that the F is constant work itself. Otherwise, we have to count the work for evaluating the F itself, but let's assume that's constant. So what do you think the work should be here? No, N, yeah. Should be the size of S, right? Because I'm going to have to at least apply this function to every single element, so that's going to take at least the size of the data. And certainly if I did this on lists sequentially in Lisp, it would take linear time. You'd go down the list, keeping the ones you care about and not the ones you don't. So that's going to be the goal. And the span, someone mentioned log n, so that's correct for the span. My goal is going to be log n for the span. So the question is, how do I do this? It's a puzzle. What did you say?
You can first do the parallel map and then parallel reduce.
How do I do it with parallel reduce? So you're exactly right. I can do a parallel map in order to, for example, get these flags.
Yes.
then how do I do it with a reduce?
You just did the append if there is true.
Good. Okay, so that actually is one way to do it. That's a good observation. I can actually do a reduce append. So that's a very keen observation. I could do basically
When you write into the list, you need to maintain a counter where multiple processors would be writing to that list.
I don't have any notion of processes here, so I don't have to use any count. This is all in a purely functional setting.
We are computing this in parallel, right?
Yes.
So if you could have a processor, you can have threads or cores.
Yeah, but at the abstraction level we're working at, we're not thinking about cores and threads. So the idea is what we're going to do is we can take these, and everywhere it's true, we can return a singleton. So I can easily write the code that says, if true, return a singleton of the corresponding element. If false, return an empty set. Right? So I could return this, and then I could return, this would be empty, this would be empty, this would be D, this could be E, this could be empty. Does everyone believe we can do that with a trivial tabulate? Right? We just tabulate over the locations, evaluate the function. If the function is true, we create a singleton. Otherwise, we create an empty. And the function is constant work because creating a simple singleton is constant work. Okay, so we can generate this in order, basically size of S work and order 1 span. So this is what you were suggesting, right? Mm-hmm. And then I can do a reduce append on this. So if I take this and I say reduce, I guess reduce takes an identity element, which is for us is just the empty sequence. By the way, I write sequence with triangle brackets around them. Umut writes them with circular brackets, but so technically this should be a sequence of sequence. It's a nested sequence. So, what? So reduce this and then append, and I claim we're done. Right? We're just going to append all those things together. Append is a associative function. Okay? So that's a solution. So very good. So the question is, do I get my bounds here? I claim I actually do get my logarithmic bounds because we just showed that reduce is logarithmic span, and the append is constant span. So if we just add that all up, I do get logarithmic. This is going to be logarithmic span. So if we care about what this code takes here, and this is going to take span is going to equal order log n. Can someone tell me what the work is? The issue is that the append is this exactly high order thinking, right? We're no longer, the function f we're applying is no longer constant work, right? Because if it was, so what Umut said is, if this function is constant work, then append takes linear work. That function is not constant work. In particular, when we get sort of to the root, remember the way that either the divide and conquer or the contraction basically will end up pairing them up in some way and build a tree. When we get near the top of the tree, it's actually linear work. Because we said append, we go back to the cost of append here, right? It's linear work. Okay, someone tell me what the work of this piece of code is. It's not n squared. N log n. And the reason why is if you look at this tree, there's log n levels of the tree. That's why the span. Each one can do n work total. Because the total length of all the sequences, right? At the next level, these two will be combined. The total length across all the sequences are going to be at most the number of original elements. And so I'm going to do at most n work total on each level, and there's logarithmic levels. So here's where the analysis starts getting tricky, right? So here's where our sophomore students start scratching their heads and going home and thinking about it for a while and figuring it out, right? Because no longer the arguments, I can't even write a clean recurrence for that. I have to argue it slightly differently. I have to argue that the total amount of work on each level of recursion here is linear. And the total is therefore n log n. So this is going to give me work which equals order size of S log size of S or something. And so we don't get work efficiency. So that's a very good suggestion, but it doesn't quite satisfy our needs. So the question is there a way to satisfy our needs? Oh, and the way the boards work, I'm going to have to reuse the one above. Okay, let's just remember that what inject does, because I'm going to be using inject. Okay, so any ideas of how we can get linear work?
So if we map 2 to 0, 1 and false 2 to 0, and then do a prefix sum, then all the indices and values will be passed into the
Inject. Yeah, I told you to remember it and you forgot it, but perfect. That's exactly right. Yes, inject takes, remember, an array and a sequence of updates, a sequence and a sequence of updates. So, exactly right. So the point is, what we have, and so let me repeat what was just said there, is what we have is this sequence of flags, right? We had the true, false, false, true, true, right? And what we know is that this element is going to go, because at the end we're going to write out the, what is it, A, D, and E, right? So we know that this element at this position, let me write, I'm going to unfortunately have to copy the whole thing down, B, C, D, E, and G. So we basically want to write these elements, some subset of them, into this sequence here. In particular, we want to write the A into location 0. We want to write the D into location 1, and the E into location 2. And these ones, well, we don't care where. They don't go anywhere. So with my inject, I can possibly do that. I can say, well, if I can figure out this 0, 1, and 2, and if I can do an inject, I can then pair them up. I can say 0 and A, and 1 and D, and 2 and E, and say write E to 2, write D to 1, write A to 0. It turns out it's a little messy what I have to do with B, C, and G. And there's maybe cleaner ways to do this, but I'll show you a way to do it. And so once I do that, then I write A to 0. I would get this. I would write D to 1. And I'd write E to 2. And that's what I'd get. And the inject itself only, remember, takes linear work in the size of these two things. And they're certainly both at most the size of S, right? A is the size of S, and is actually less than the size of S, or maybe depending exactly what we're going to write. It's certainly no more than the size of S. So if we can do that, it's scot-free. So here's a perfect example of where the prefix sum helps, right? Because this, if I convert the trues into zeros and ones, right? So if I replace TF, TF, TF with, let's put the zeros and ones. trues are ones and falses are zeros. So basic, if I think like a C programmer does, then those are already at zeros and ones. I don't even have to convert them, right? So then I do a prefix sum, and I get, zero, a scan operation, 1, 1, 1, 2, I guess 3. And all I care about is these 3 locations, right, where it was true. And I've got the right offsets. Is that clear? Any questions? Yeah, so at this point, everything I'm doing here is just building up on what we've already done. I can do effectively a map to get from here to here. In fact, I can skip directly to here if I want. So I can write down the code for this. Fun fill to FA. Let up here. First, I'm going to take, I'm going to say, I'm going to generate my flags, which are going to be actually zeros and ones. So flag is going to be basically map over, I'm going to map it over my sequence A. Make this a capital A here. But the function I'm going to map is going to be something like fn of x. Fn of x, of course, is equivalent to lambda x. And we're going to map it to either x. You say if f of x, then 1, else 0. And we map that over A. Then I do a scan on this. So maybe let's call this off for offsets. I do a scan starting at identity 0, op plus to mean the plus function, and I do it on my flags. And scan actually, if remember, it returns 2 things. It returns the offset and the total. So let me put that at. So it's off and total. So now I've got this. This is basically my offsets here. This is my flags. And then I want to generate my input, my U's here. So I have to basically pair things up. Okay, so I'm going to generate U, and I'm going to do that with a simple tabulate. And it's going to return offset I, where I want to write it, and my value I, which is the thing I want to write, which is AI. And this is going to be over the length of A, I guess. And I pretty much now I just do a big inject. Now there's a little bit of magic that's going on here, and someone can complain. And we'll visit that in a second. So what I do is I first generate some dummy thing. And this is, well, first of all, this is cheating a bit. This assumes the length of my array is not 0. I'm going to basically generate a, I'm going to generate a array of some element which I'm going to inject into, and I don't care what that element is. So let me just make it the 0th element. Of course, this will fail if A is of 0 length, but I can put a condition in there, or I could fix it in various other ways. And we want to create something that's, this total here is the total number of things which were true, right? So this would have returned, if I do a scan on it here, it would have returned this as an offset, and it would have also returned 3 as the total number of things which are true. which is the size of my output. So this tabulate here is just going to generate basically a dummy sequence of any element into that my U's, and that's it. So what's the one fishy thing about this? I'm injecting everything, so I'm injecting, I'm not filtering out, so in this case I'm injecting B into location 1, I'm injecting C into location 1, okay, and I'm injecting G into location 3. I claim 2 of those are perfectly okay because we had the rule of inject that the last one wins, right? But technically what I would probably want to do here is, which I just left out, I do want to trim off and I want to make sure that this doesn't get written to location 3 because that might just cause an exception. Okay, so I'm going to leave that out. And that's why I say it's maybe not as elegant as ideal, but it should be clear that I can check if it's location 3, and then the rest of this would all work. Okay, so and I claim that this has my bounds. Why? Because I can just go step by step. This is linear work, this is linear work, this is linear work, that's linear work. This one's constant span, logarithmic span, constant span, logarithmic span. Remember, I defined the span of inject to be logarithmic. So the total span is going to be logarithmic, and the total work is going to be linear. So any questions here? Yeah?
Sorry, in the scan line, what's right after the 0?
Okay, this is SML notation. I think Umut did it the better way, which was, well, I guess he did it with lambdas. Lambda x comma y equals x plus y. A. In SML, you can say op before a infix operation, and it means treat that infix operation as a function. It's just some SML magic. So apologize for using SML magic. Okay, any questions on that? Okay, we don't have a lot of time left, so let me just mention one other routine, flatten. And I'm going to give you, just like the pack or the filter, there was one way to do it that was log n off in terms of work. We can do a flatten very easily with being a log n factor off in work, and we'll leave it as an exercise for you. So I'll just state it now, and it'll be an exercise for you to figure out how to do it, just like we figured out how to do the filter in linear work, how to do the flatten. Okay, well first let me define what flatten is, although perhaps it's obvious what it does. In fact, when I write it down, the type down for flatten, basically there's only one thing it could do. Okay, because, well, I guess it could do various bizarre things, but there's only one sensible thing it could do. And it turns out to be a very useful operation. Okay. And what it does is it basically takes a sequence of sequences and flattens it into a sequence. So if I have some sequences, and each subsequence might be different lengths, and outputs the same elements. So the output's going to be the sum of the length of all the interior sequences here, right? So if there was, A, B, maybe this could have been empty, this could have been C, D, E, F. The output's going to be A, B, C, D, E, F, A, G, H, or something. Does anyone have an idea of how I would do this in let's say I was willing to spend basically the size, the total, the work I wanted to, sequentially basically what would we have to do? We'd have to append these all together. It would take me basically time proportional to the total number of elements. So the sum of the lengths of the subsequences here. And so we'd like to get that. But I can easily do this within a factor of log n. In fact, we've done it already. So how would I flatten this into that? Is what? To do what? Sorry?
You apply length on every element.
Yeah.
And on that sequence, you do a prediction. So we get indices.
Yeah, so now you're getting, okay, now you're getting at the one that's actually work efficient. Although it's tricky to get that right. So but that's your aiming, so that's very good. So you're now thinking of immediately how to go to a version that would be linear work. Okay, but it turns out to get that to work exactly right, you have to think about it a bit. But that's the direction you're going. Okay, but there's an even more naive method.
It's like reduce append.
Yeah, it's just a reduce append. It's what we did up there. So this could be just defined as flatten of A is simply reduce, I guess, with an empty sequence, append A. And the same argument as we argued above. In fact, it's sort of what we did in the middle there, is, right? We basically created all of our singleton sequences, and then we did a reduce append. It was a special case there because everything was only 0 and 1 length, but it makes no difference to the analysis, is that this is going to be, the reduce is going to be log n levels. We're going to do no more than linear work on each level. And so this is going to give us something that's order, let's say R is the result. So it's the size of the result, because we care about the total number of elements. Log, and it's actually log of the size of my input. So log of size of A. Is that's going to be the work. And this span is going to be order log n. For the same reason as we argued up there. So the thing is to notice here is that we can build up, once we have reduce and these different things, we can very easily build up more interesting operations. In this case, it might not be perfectly, optimal in terms of work, but it's certainly a very easy way to write. And it's very parallel. In terms of the span, this is as good as we possibly can get, this log n here. Yeah.
Sorry, what's R again?
R is the size of the result.
Oh,
It is the result.
which is a sum, yeah.
Okay. Size of R is so the size of R, another way is to say the size of R is a sum for every I of size of, AI or something like that. It's sum of the lengths.
And is number of total elements or number of subsequences? Number of,
Good. So n here is actually the depth of recursion of the reduce is only going to be the size of my original sequence A. So this is actually not, it's log of the size of A as opposed to the size of, so for example, if I was doing a flatten and it happened to be I only had 2 subsequences here, or 3, some constant number, this is actually perfectly efficient because this would be log of 3, which is a constant, right? So if I have a constant number of subsequences, I don't even have to worry about doing anything fancier. I'd be happy with this. Okay, and the span would also be just constant. In fact, I could just append them all, and it would just be constant total span and constant and linear total work. Okay, because this is going to be the depths. Because what I'm going to do is I'm going to do a reduce, and the reduced tree is going to be on these elements here. So if there's only 3 of them, the reduced tree is only 2 high. Okay, so I think it's noon, and I don't want to hold you off from.
Before you finish, I
Okay.
want to highlight something about what you.
Okay.
I just want to connect what you.
Okay, sure.
Just.
Go ahead.
I'll just need a second. So, remember in the first lecture, we briefly talked about how update is expensive, right? If you do a single update, it requires linear work because it tabulates in constant span. It's constant span, but it's linear work, very expensive. And you'll hear a lot. If you go talk to people, they will tell you, well, function programming doesn't work because an update takes linear work. It copies the whole thing and so on. Now, well, to implement filter perfectly efficiently using linear work, log and span, we've used updates. In fact, we've used many updates, but we still didn't break the bank. And that works because what I said in the first lecture was, in parallel algorithms, you don't do updates one by one. You're doing a bunch of updates at the same time. If you're doing updates one by one, your algorithm is not parallel. You can see that in the way that guy did the filter. You do an update, but your update is a bulk update. It's an inject. That does a bunch of updates at the same time. And therefore, the cost of updating gets amortized over the many updates that you do, and you get perfect efficiency. So that's something like an important lesson, is that parallelism is an antidote for side effects.
Okay, good.
Thank you all.
Thank you.